Geçen ders so last time we were discussing this theorem or proposition. Whenever we have a complete metric space and a dense subset A of it, well, okay. Y is complete, X is any metric space, and A is a dense subset of it. X doesn't have to be complete. And we have a uniformly continuous function defined only on the subset A. The content of the proposition is the following. And this function has a unique extension to x. Okay, so I can extend this function to x uniquely so that the extension is also uniformly continuous and the two functions agree on uh, uh, at all the points of A. Well, that's the meaning of extension. Further, if F0 is an isometry, then this unique extension is also an isometry. Then I gave some examples where you drop some of the assumptions, and in that case, the conclusion of the theorem fails. For example, here, okay, this is a dense subset here, Y is complete, there is no problem with that, but F0, although it is continuous, it is not uniformly continuous, and therefore it cannot be extended to all R. Okay, that was an example, and here is an example. This time uh, F0 is identity function, it is uniformly continuous. However, Y is not complete, and therefore it cannot be extended to real numbers, right? It takes all rational numbers to itself, right? X goes to X, but then what about irrational numbers? There is no place for irrational numbers, uh, you know, to be mapped in Y. That's why F0 cannot be extended to R. And then we started the proof. First, we defined the function f on x. How did we do this? Well, since A is dense in x, for any x, we pick up a sequence, Cauchy sequence, which converges to that element. And then we use that Cauchy sequence to define f at that element. And the observation is that if xn is a Cauchy sequence in n, in A, then its image under f0, which is a uniformly continuous function, is also a Cauchy sequence. Okay, we proved that, and then we define f at any point. So I pick a point. Since I have this, I choose a Cauchy sequence which converges to that element. By the above result, we know that its image is a Cauchy sequence. And since Y is a complete metric space, it is convergent. So this sequence is convergent. And I define f of x as the limit of that convergent sequence. But there's this issue that, whether this is a well-defined, function. What does this mean? If I choose another sequence which converges to the same element, I have to prove that these two limits are the same, because if I use this sequence to define f, I will get some result, and if you choose this sequence to define f, you will get another result, and this is not acceptable, right? A function should have a well-defined value at every point. Okay, it shouldn't depend on the people or the sequence you choose. So we have to prove this fact. Do you have any questions so far? So, okay. How can we prove this? Whether these two limits are the same or not? This is how we will proceed. Okay. Uh, so our aim is to prove to show limit f0 yn is equal to limit. Maybe I give numbers to this. Okay, show that if L1 is the limit of f of xn, f0 xn, and L2 is limit of f0 yn, then L1 equals L2. This is what I need to show. All right. Well, so let epsilon be given. Okay. Choose okay. Choose delta positive so that whenever xy in A are so that the distance between them is less than delta, then rho of f of x y. Well, since these are in A, f is equal to f0 in A, right? So this is actually equals to this. This is less than epsilon over 3. I can do this because f0 is uniformly continuous. This is possible since f0 is uniformly continuous. Okay, f0 is uniformly continuous. You give me some epsilon. Well, epsilon over 3 is a positive number, and for this epsilon over 3 I choose delta, so that if x and y in A are delta close to each other, then their images are epsilon over 3 close to each other. Okay, and then we do what? Well, since limit of xn is equal to x0 and limit of yn is equal to x0, right? This is how we choose both xn and yn converges to x. Yeah, not x0 but x. I have to be careful. Okay, these are x. Both xn and yn converges to x. Since I have this, I can find and then choose. We may choose. Let's say n1, so that n greater than n1 implies both this limit, I mean this xn x is less than delta over 2 and d of yn x is less than delta over 2. I can do this why is that? Because there is some actually index for this sequence, so that after that index this distance is less than delta over 2. There is another index, so that if n is larger than that index, this is less than delta over 2. And I just choose n1 to be the maximum of these two indices. Okay, so there is one n0 for this, there is another n0 for this, and I choose n1 to be the maximum of these two n0s. All right, and one more, I have also uh, this limit. Moreover, since limit of f of xn is equal to L1 and limit of f yn is equal to L2, there is some n2, so that just the same, you know, similar thing. If n is larger than n2, so this implies the distance between f of xn and L1 is less than, let's see, epsilon over 3, and the distance between f of yn L2 is less than epsilon over 3, right? Again, actually what I do is the following. There is some n0 for this limit, and there is another n0 for this limit, and I just choose n2 to be the maximum of these two n0s. All right, so that if n larger than both of them, both these limits, both these distances are less than epsilon over 3. Now let n0 to be the maximum of this n1 and n2, so that if n is larger than n0, all these inequalities will be satisfied. All right, so if n greater than n0, then we have what? Then, well, first of all, this distance is always positive, and I write this. This is rho of L1 and then f of xn plus rho of f of xn, f of yn plus f of, sorry, distance, rho of f of yn and L2. You see, if n is, since n is larger than n0, it is larger than n2. If it is larger than n2, then the first term is less than epsilon over 3. So this is less than epsilon over 3. And this term is less than epsilon over 3. What about the middle one? N is larger than n1 also. And if it is larger than n1, then both of these numbers are less than epsilon over 3, epsilon over 2, and actually this implies, and actually maybe I should write this here. The distance between xn and yn will be what? Well, this distance is less than the sum of these distances by the triangle inequality x to yn, but this is less than delta over 2, and this is less than delta over 2, so this distance is less than delta over 2. Sorry, delta. However, if these are less than, if these are delta close to each other, then their images, right? Their images are less than epsilon over 3, right? The distance between the images is less than epsilon over 3. So this middle term here, this is in A, this is in A, and the distance between them is less than delta. Therefore, this is less than epsilon over 3. So we get a delta. So what we have seen is this. Hence, I have this. This is a positive number and it is less than any epsilon, any positive epsilon. So hence, by the epsilon lemma, this distance is equal to 0, and hence, and thus L1 is equal to L2. So we are done with the well-definedness of f. Okay, these two limits are the same. So f is now a well-defined function. Therefore, f now from x to y is a well-defined function. And how is this defined? Whenever you pick an element here, you just choose some xn in A with limit xn is x, then f of x is just limit of f0 of xn. Okay, this is the definition of f. Okay, any questions so far? This is one of the most how to say you know complicated proofs in this actually course, because it has several steps. Each one is maybe easy, but you have to, one has to be careful. Okay, well, what else? We claim that there is an extension, unique extension. I just proved that there is an extension. I have to prove still that it is unique and it is uniformly continuous. All right, so the next thing we will prove is that f from x to a, x to y is uniformly continuous. Okay, how can we do this? Well, arguments are similar. Uh, let epsilon be given. Again, since f0 from, sorry, a to y is uniformly continuous, this is given, uniformly continuous. There is some delta 0 so that distance between x and y less than delta 0 implies the distance between f of x and f of y is less than epsilon over 3. Here, of course, f or f0 doesn't matter because f and f0 are the same at all elements of A, right? So I write here f0, but here I write f because they agree on A. We know that. Okay. Actually, how do we know this? Well, you see, if x is in A, then I can choose my sequence just to be the constant sequence, okay? Constant sequence. So f of x, which was defined to be f0 of xn, but xn is just x. I choose xn to be the constant sequence, okay? Constant sequence. So this is just limit of uh, okay, the constant element, and this limit is of course just that constant element. So f and f0 agree on A clearly. All right, now how we will proceed? I choose some delta 0 so that this is uh, satisfied. Now we choose sequences xn and yn in A with this limit conditions. I choose these because, to define f at x and y, right? X and y are just okay. Okay. All right. We know that we know limit f of xn is equal to f of x, and limit f of yn is equal to uh, f of x. So hence there is some n0 as before, so that n greater than n0 implies both this is less than epsilon over 3 and sorry, why here? All right. Okay. All right. Oh, okay. I choose this n0. These so that these are satisfied and these are satisfied. In particular, so for each all these limits, right? I have four limits. Xn converges to x, yn converges to this number converges to here, and this sequence converges here. For each of them, there is n0, and this n0 will be just the maximum of all those n0s. In particular, we have the following. In particular, if xy in x are with dxy less than delta 0 over 3, then this distance dxn0 yn0 is less than dxn0 x plus uh, dxy plus dyn0 y, and this will be, all of them are less than delta 0 over 3, so this is less than delta 0, and I choose delta to be delta 0 over 3. Then if dxy is less than delta, then I have what? Then we have this rho of f of x, f of y will be less than what? This is f of x, f of x and 0 plus rho of f of x and 0, f of y, no, y and 0 plus rho of f of y and 0, f of y. Well, uh, now all these gadgets are less than epsilon over 3, right? Epsilon over 3. Therefore, uh, this is less than epsilon over 3. This is less than epsilon over 3. And the third one is less than epsilon over 3. And we are done. But actually, I cheated a little bit. Let me tell you why I cheated. You see, I have to be more careful actually. So when you give me this epsilon, okay, I choose this delta 0, so that this is satisfied. But this is not the delta I am using, okay? I will use this delta. So my delta is this, okay? I choose delta this. Now, if x and y are delta close to each other, then this is what I'm doing. I go back and remember how f was defined. So I choose my sequences, okay, convergent to x and y, because you know I picked x and y. For this x and y, I choose sequences, and I have my epsilon and delta 0, delta. I choose this index n0 so that all these inequalities hold. And then I come here and I use that n0. You see here there is no n0 and there is no n0 here. I just use this n0 in between, okay? So actually the way I write the proof is not 100% correct. Uh, uh, but uh, I wrote it this way so that it is actually easier to follow, but this is how actually it should be uh, considered. This is given, epsilon is given. I choose delta to be delta over 3. What is delta over delta 0? uh, Delta 0 is the uh, delta for f0 for this epsilon, right? This is a uniformly continuous function, so whenever I am given some positive number, I can find some delta and so on. All right. So this is how it actually works. And then whenever I choose x and y, I go back, find sequences, uh, so that all those inequalities holds and so on. So we have proved what? I was given epsilon. I found my I can erase this part. My delta is this, and if x and y are delta close to each other, then this is less than epsilon. Okay, so this finishes the proof of the claim that f is uniformly continuous. Hence, f is uniformly continuous. All right. What else do I need to prove? There is uniqueness of f. Okay. Well, we were given f0, and we found f, and assume that there is another extension. So uh, assume that f tilde from x to y is another uh, uniformly continuous, or just even continuous, is another continuous extension of f0 from a to y. Okay. Let x be, so what I must prove, we must prove this. Okay, we must prove f tilde x equals f of x for any x in x. All right. How I do this? Well, take any x in x and choose some xn in a with the limit xn is equal to x. Well, then f of x, f tilde x is equal to what? Well, since this is a continuous function, it is equal to the limit of this sequence, since it is continuous. However, f and f tilde are the same for any point in A, because f tilde is an extension of f0, right? It's an extension of this. It means at any point of A, f0 and f tilde are the same. And this point, xn, is in A. Therefore, this thing is equal to f0, okay? But f was another extension of f0, so this thing is equal to also f of xn, because f is also an extension of f0. And finally, since f is continuous, this is equal to f of x. So f tilde x is equal to f of x for any x. Okay. Hence, the extension f of f0 to x is unique. Okay. The continuous extension. Okay. I don't even use the fact that they are uniformly continuous. Continuity is enough. Okay, so we have to prove only one last thing, that f is an isometry if f0 is an isometry. Finally, we will prove that uh, f x to y is an isometry provided that f0 from x to a to y is an isometry. Okay, let's see why this is true. Actually, this is just the triangle inequality. Uh, let's see how it works. Okay, let xy be in x and choose sequences xn and yn in A with limit xn equals x and limit yn equals y. I have this. Note that uh, dxy is less than. We have actually done this kind of stuff before, but let me rewrite it. I have this, right? Distance from x to y is less than the distance between x to xn plus the distance from xn to yn plus the distance from yn to y. And this implies what? This implies dxy minus dxn yn is less than d of this distance plus this distance. Now replace x and y in each of these. If I no replace x and xn and y. Okay, maybe I should say with xn and y with yn, right? To get what? If I do this, I will get this term will be xn dxn yn, minus dxy. What about this? If I replace x and xn, this won't change, okay, because metric is symmetric. And if I replace y and yn, again this won't change. So what I obtained is this. The right hand side of the inequality didn't change, but the left hand side is multiplied with -1, right? This is multiplied with -1, but this didn't change. So this implies what? Hence, the absolute value of this expression is less than this, because both itself and its negative is less than this expression. Hence, its absolute value is less than this. Right? Absolute value is either this number or this number, but they are both less than this. Therefore, I have this. Now, okay. So, uh, okay, this implies what? Since limit xn equals x and limit yn equals y, uh, given epsilon positive, there is some and 0 so that n greater than n 0 implies both these limits is less than epsilon over 2 and right. I choose n0 for each of them and then I take its maximum. Well, since these are both less than epsilon over 2, then this distance is less than epsilon over 2 plus epsilon over 2. Hence, dxy minus dxn yn is less than epsilon. This means what? You see, given epsilon positive, I found some n0 so that if this is larger than n0, then this is less than epsilon. This means what? This means thus limit of dxn yn is equal to dxy. Okay. Well, similarly, in the other vectors, in the other metric space, similarly, I know that this converges to f of x and this thing converges to f of y by the definition of f, and hence so the same arguments in the metric space y implies, so the same arguments imply that the limit rho of f of x and f of yn will be rho of f of x f of y, okay, in the metric space y rho. So hence this distance, which is just the limit of but I know that since x and y and are in A, this thing is just f0 x and f0 y n, but f0 is an isometry, therefore this distance is the same as the distance between xn and yn. Okay, here f0 is an isometry, but we show that this limit is just dxy. So we have seen that this distance is equal to this distance, hence f is an isometry. Okay, okay, so this finishes the proof. Which was quite long, right? It took several pages, but finally we managed to finish the proof. Okay, so right, we finished the proof of this proposition. Whenever we have a complete metric space and a function to that metric space from a dense subset of a metric space, another metric space, uh, we can extend this function uniquely to a uniformly continuous function, provided that the function we started with was uniformly continuous. This extension is unique, and moreover, if f0, the function we started with, is isometry, then the extension is also an isometry. Okay, and this is the proof. All right, this is basically the same proof in the book, maybe slightly different. I think I put more details in the proof, but almost the same proof, and you may go and read the one in the book also. Okay, now let me stop here.